So next are Sergey, Kachkin and David Villa on optimizing Lustre throughput in a software environment, configuration tips and performance insights.
Sergey Kachkin is the performance engineer at Xenor and focused on software RAD solution on Linux, performance testing and tuning in collaboration with Linux kernel development, and also specializes in Lustre file system benchmarking and tuning. David Villa is the Chief Revenue Officer at Xenor. Xenor is an Israeli startup that develops the fastest software RAD engine for NVMe SSD.
Okay, thanks everyone. So I'll speak just for a few minutes, then I will hand it over to Sergey, who has all the technical knowledge that you want to learn today. But since we are not a big organization, I wanted to just set the stage and explain a bit who we are before going into the main topic of today's conversation. So Xenor is a startup. We were founded just 1 year ago, and we were founded out of Israel. But we are a very unique startup because we are leveraging more than 13 years of development, software development in the fast RAID implementation. We inherited all the intellectual properties that were developed back then by a company called Radix, and now we are the owner of all the international IP that were developed by Radix. Our mission is to develop the fastest software RAID in the market. And since we are talking about being the fastest, we are starting from NVMe SSD, but we are also deeply involved on HDD projects. We are about 40 people, most of them in development. I'm a CRO, but DR might stand for RAID, more than revenue. And we have something like 20 partners already worldwide, growing, and we work with all the major SSD vendors because we are starting from NVMe. So we have a relationship with basically every SSD manufacturer. And we are a startup, but we already have more than 100 petabytes of data that are protected by our fast RAID engine. Last summer, in August, we were awarded the Best of Show at Flash Memory Summit for an implementation that we did with Western Digital and BGFS. I understand this group is more on Lustre, so let's talk about Lustre. So in our company, we have two main products. The core of our technology is the RAID engine. We claim we have the fastest RAID engine in the market, much faster than hardware RAID, because hardware RAID is limited when you deal with the high level of parallelism of NVMe, and faster than open source software RAID, much faster than MD RAID. But also, it's not just about the performance, it's also about the CPU efficiency that we can achieve. And then the other leg, and this is where Sergey will focus mostly, is that we are using our software RAID to build a tailor-made solution in the HPC space. So our largest customer is the largest scientific institution in Japan, and we are developing for them a solution which will integrate self-made decluster RAID for NVMe, but also for hard disk drive in a HA configuration running Lustre on virtual machine. So with this, let me hand it over to Sergey, who will dive into the topic of the presentation.
Hello, as David said, we're a storage company, and I'm primarily a storage performance engineer. And now I'm doing a lot of Lustre tests, and I'll talk from a storage engineer point of view about IOR, bandwidth intensive tests, so no millions of IOPS, no metadata intensive things. And I'm going to talk a bit about workloads, about our experience from testing, and some challenges and actually questions that we got. Let's start from the workload. As storage engineers, we run benchmarks a lot. And what I've noted, benchmarks typically try to emulate real workloads. That's obvious. But on the other hand, application developers, they often look at benchmarks and try to emulate the I/O pattern in their applications. They want to get the same hero numbers. And so it works in two directions. It makes benchmarks more important. And here is on the slide a very simple test that we very often run when we test storage. What we can see here. I'm sure if it works. Here we have asynchronous I/O. So we have I/O parallelism. We have 1 megabyte block size, and I like it because it's well tested in Linux kernel. Many people use this block size, and if something is wrong with 1 megabyte, it will be fixed very quickly. And we have I/O depth of 32. And this is also good for storage because it's constant. And we can control the storage utilization by increasing and reducing the I/O depth. So from a storage point of view, I like this workload. Now let's take a look at IOR. I got this from our customers and also from Google, so I brought some presentations. So I hope that I'm not totally wrong, that these patterns are common. First option is direct I/O, and typically very large block size is used to get I/O parallelism, because this large block is split into many small blocks. This is good. So we somehow can control how many I/Os in flight we have. But the downside that this workload is bursty from a storage point of view. We send a batch of I/Os to storage, then we wait for them to complete, and then we send another batch of I/O requests. So we have spurts of I/Os and then periods of idleness. And from a storage point of view, it's not easy. Another option is buffered I/O. It's good that it is asynchronous because of client cache, but the downside, it is difficult to control how many I/Os we have in flight. And it's what I've noted, it's very easy to overload with disk subsystems, and you need to play a lot with many tunables to throttle the workload. So both options from a storage point of view, they're challenging. And what I've noted, it is better to tune the system and play with FIO micro benchmarks before moving to IOR. Few words about setting expectations before we started any testing. It is good to get any goal, to at least some numbers in mind where we're going to. And the only source for performance numbers for media is datasheet, and typically we have sequential and random numbers. So, and I would read it as hero number and villain number. Why? Because typically, not typically, I think it's always, for SSD, performance is measured according to SMIA methodology, and it's measured in steady state. So drives are preconditioned, and we run the same test many times, and don't change the workload, and so on and so on. But when we run IOR tests that are typically short, and we don't do preconditioning, and we do FStream to free some blocks at media, we never know at which state the media will be. So if we do FStream, we probably will have performance even better than steady state documented, if we're lucky. But if we don't do it, for some reason, I don't know, file system is full or FStream doesn't work or whatever else, then performance may be lower. And the worst case, we go to something like this. So basically, we take hero number. And after we got performance of a single media, we can calculate expected performance of a single RAID. This is very simple, but I found it is very valuable. So we multiply performance of a single drive by a number of data drives. And then we get some number, which is maximum theoretical performance of a single RAID instance. But in real life, we normally have from 80 to 90% of this value. Why? Because of two major factors. First of them is the software RAID overhead, or actually, because we develop software RAID. And on the other hand, media latency deviation, because we need all medias run at the same speed. But it never happens. Some of them will be slower than others. So now we have some expected performance from a single RAID instance. Now move to testing. Since we are working on a software RAID, we have direct access to disks. So this is actually gives us some flexibility because we can run many tests, we can play with tunables, we can apply some fine-grained settings, and this is good side. But downside is that it's software RAID. This is another application which is running on the server, and it will compete for resources with Lustre and everything else. So trade-off as always. And since we have direct access to disks, we can stress all disks at once with some simple workload. And we're checking two things. First one is that our hardware platform is able to provide the bandwidth that we need, that all disks run at full speed. And also, we check that performance of all disks is the same. Because even one slow disk can ruin all performance of entire system. This is how it works. After we stressed just raw disk, we can do a scalability test. I got it from, the theory goes from universal scalability law. The idea is simple. We stress one RAID instance with IO depth of 1, and then we increase it. And we check that performance doesn't degrade. So it should be stabilized at some layer and shouldn't degrade with IO depth increase. Somehow it happens very often. After we checked one RAID instance, we stressed all RAID instances at once. Again, this is a very simple thing. And we check that no influence of RAID instances. And also we run this test from the host and virtual machines, if we use virtual machines. And we compare results of this test with all the tests we've done before. And if everything is okay, and normally everything is okay, happens after some weeks of hard work. But after everything is okay, we can move to IOR test. For us, IOR test was pretty much straightforward because a lot of work was done before with FIO. And most of Lustre tunings were default. We used Lustre 2.15 and it worked pretty well. I didn't change many tunables, but I want to mention one common tuning that shows, it showed best performance for us, and I've seen that for other installations it works best as well. This is a big transfer size, 16 megabytes. It gives best performance, but on the other hand, it may Linux kernel may not like it, and it may split large logical I/O into smaller physical I/Os. Typically, I/Os are split by 1 megabyte boundary or 2 megabyte boundary, and this is okay for RAID. So not much performance impact. But sometimes, for some reason, I/O requests can be split by 4 kilobyte boundary, which makes this size is not aligned by stripe size, RAID stripe size. So it has huge performance impact. I've seen this on different Linux versions, and it happens in a random manner. And what I've learned here, if performance degraded significantly with no reason and RAID works slowly, then check the physical I/O size that goes from Lustre to disks. Bilka trace, perf, and so on, any tool works that shows individual I/O requests. Just a few things that I learned during this testing. Disable hyperthreading, because it may cause many confusions, and just disable it. Really. The reason is, again, software RAID and Lustre, when many applications on the same host, Linux kernel may not optimally distribute tasks to CPUs, and it may work bad. NUMA just pin everything to optimal NUMA nodes. Very simple. Very simple to say. If you have virtual machines, two interesting tunables. I just noted that I/O, I don't know how it's called, it's planner or just settings. I'll call this settings. I/O set to native works better for sequential patterns, because threads use pool of threads that works on different cores, and they may break sequential order of I/O requests. And native is just async I/O, and it works better. It works better. Virtual machine driver. Also, virtual machine virt.io BLK driver may cause I/O splits and merges. So it may send to disk not the same what it got from Lustre, and again it may cause not aligned I/O requests. Oh, okay, we're almost done. I don't know. Okay. This slide is about how to make stupid mistake in a simple sentence. It should be IOR. So I'm not just talking, we did tests as well. And we did tests for HDD and SSD configurations, 2 servers, 4 VMs, 12 OSTs, 500 disks. Pretty simple. I did the same tests I explained before. from raw disk, I verified that performance is stable across all drives, so everything was fine. Then I measured it with RAID, got some number, and I using calculation, as explained before, we have here 80% of raw capacity because we calculate only, we take into account only data disks. And then with IOR FPP test, I got 50 gigabytes. That was our goal actually for this testing. That's it. Okay, so this slide is about how to make 2 stupid mistakes in a simple sentence. Then, actually same with OSS configuration, but with SSDs. And this is a bit more interesting. Here, if we calculate expected RAID performance, we have 67 gigabytes per second. With IOR, we have 63. So it's pretty close to theoretical maximum. And it looks very good, isn't it, for any bidding, for good result. But what's confusing that FIO shows smaller number. And I think IOR is a bit too optimistic. I would not rely on this if I want to understand how this solution will work in real life. Because this test is short, okay, we repeat it many times, and we got it from the customer. But as I said before, we don't know what is the state of SSD. We do FStream, what will happen when the file system will be full, and so on and so on. So I think this testing leaves some open questions. And okay, we're done. What I've learned from here that IOR workloads, they are very different from traditional storage workloads that we run with FIO. And before moving to IOR, it is good to run some FIO tests and tune system with FIO. And also, the storage systems are developed with benchmarks, they are sold with benchmarks, they are accepted with benchmarks, and only at customer side they meet they meet real workloads. And this is the reason to invest time into more advanced benchmarks, and it will make the industry better. So that's it. Thank you very much.
Thanks. Are there some questions?
No? No questions at all?
Just one question, so if nobody has a question. What about HDD failure, and more specifically, when you have a bad sector on one disk, what kind of process do you use to verify that all drives are healthy? Like in software WED, you have some WED check, that's one way, and you got the same kind of tools. And the question is, what kind of impact they have on performance?
If one drive has failed?
No.
Or bad sector?
When you have an HDD, for example, when HDD is not a perfect solution, you can have bad sector on this.
Yep.
And how do you deal with this? Because on the WED stack, if you can't access to this bad sector, that's a problem. It's an issue.
We have a scrubber. That, no, I think scrubber will not help here. I'm not sure if a single bad sector will have, or not, some bad sectors will have any impact, but if one drive is slower than others, that entire rate will be slower, and we need to somehow to market this drive bad and reconstruct the RAID. Since we use the clustered RAID, it typically happens quite fast, and then you just replace the drive. I'm not sure that I understand.
No, there is a difference between when you fail a drive and you have just one sector which is failed. And it's life of an AGD, for example.
Most likely, this drive will be slower than others, and
you kill him.
Well, yes, the only solution is to kill it.
Okay.
To mark it as a fail and replace. Yep.
Okay, thank you.
No.
Other questions?
No?
No.
Okay. Thank you.
Thank you.